So today we're going to start off with a presentation by Lauren Zamora. Lauren is at NASA and she has been working with satellite data in the Arctic to quantify aerosol impacts on clouds. So Lauren is going to give us an overview of a range of things she's been working on in the past year or so. Lauren, we'll pass it over to you.
Great, thank you. Let me just pull up the... Can you see my screen?
Yes.
Okay. All right, well, thanks everyone for coming and joining in to hear what I have to say. So today I'm going to be talking, as Allison said, about quantifying aerosol indirect effects over the Arctic. And before I get started, I just wanted to acknowledge my collaborators, and in particular Ralph Kahn, who's my supervisor, and he's been closely involved in some of this work. And I'd also like to acknowledge the people whose data that I've been using listed here in the acknowledgements, just because without these data I couldn't possibly do this kind of work. And lastly, I wanted to also just acknowledge our funding sources. We're funded through a combination of Ralph Kahn's grants from NASA's Climate and Radiation Research and Analysis Program under Hal Mehring, and NASA's Atmospheric Composition Modeling and Analysis Program under Richard Ekman. And there's actually Richard Ekman who suggested that what I have to say might be of interest to the Arctic community, and who facilitated this opportunity to talk with you guys. And this work was originally started also from a grant from the NASA postdoctoral program. Oops. Oh, I'm having trouble. Okay, there we go. So just a little bit of background. Everybody already knows this, but the Arctic is changing rapidly, and it affects all kinds of important processes and things that humans care about, like shipping and weather, sea level rise, fisheries, wildlife, and a whole host of other things, some of which are listed here. And so that's why one of IARPIC's goals is to improve the improve surface radiative flux information. But unfortunately, a lot of the models can't really simulate. I'm sorry, is there a way to get rid of this bar? Can you guys see the bar at the top? Or is that just me?
Actually, the screen looks fine to me.
Oh, okay.
Yeah, we can't see it.
Bar at the top of my screen. All right. So clouds are a really important part of the story for understanding radiative effect at the surface. But the models have a lot of trouble simulating the cloud radiative effect, as shown by this figure here from Carlson and Svensson 2013, where you can see that there's a very large range in how well the models approximate this parameter. And it's on the order of 20 watts per meter squared. And where we really want to be is somewhere around 1 watt per meter squared. So we have a long way to go. And a big part of this uncertainty has to do with aerosols. Why am I? Okay. So you're probably familiar with this figure from IPCC, and it just shows that the cloud adjustments to aerosols are one of the largest uncertainties in radiative forcing. And so that's going to be the focus of this talk, is how aerosols are affecting clouds specifically over the Arctic. And even outside the Arctic, this is the reason why the uncertainties are so large, is because it's a very difficult problem. We have, for example, if you're looking at using remote sensing data, we have imperfect proxies for things like cloud condensation nuclei, CCN, and for ice nucleating particles, abbreviated here, INP. And meteorological covariation is also a concern. So that means, for example, when you have aerosols coming in from out of the Arctic and being transported into the Arctic, they might be associated with air masses that are moister or drier or warmer or different in some other way than Arctic ambient air. And so it's difficult to understand the confounding, or to peel apart the confounding meteorological factors from the aerosol factors. And then on top of all that, we also have nonlinearity of aerosol cloud responses. So for example, if you have a certain amount of aerosols added to a clean environment, the response of clouds might be different than when that same amount of aerosols is added to a polluted environment. And so that makes the understanding these aerosol cloud interactions very difficult. And in the Arctic, it's a little bit even more difficult, especially with remote sensing data, because you have long periods of darkness in the winter, and you have low thermal and visible contrast between the surface and clouds. And then you also have this prevalence of multi-layer clouds. And for example, this image in the background is an image from the ArcTAS aircraft campaign. Just shows the aircraft flying between 2 layers of multi-layer clouds. And this is very common in the Arctic. And then also we have limited validation data because of the harsh in situ sampling conditions. And it's also just a very complex system. This is a figure from Morrison et al. Just showing a bunch of the different important pieces in understanding aerosol cloud relationships. So some of them I'm going to be talking about today. These I've highlighted in red here. And these include CCN concentration, droplet size, liquid fallout and evaporation, surface radiative heating, supercooled water, cloud ice. And then highlighted in blue are some of the kind of things that I'm going to touch on, which also include ice formation and surface moisture and energy flux. So our goal was basically to better understand indirect effects of aerosols on Arctic clouds. And we've made some small progress. I mean, obviously there's a huge amount of work left to do, but our approach has been basically starting with some of the easiest conditions and working from there. So we started looking at predominantly liquid clouds. And first we constrain the clean cloud characteristics in detail, starting from aircraft data where we have the best constrained data, and then moving forward using remote sensing data, which have more frequent coverage and more extensive coverage. So to begin with, we used aircraft data from a variety of different campaigns listed here, ArcTask campaign, ISDAC campaign, and also 2 fire race campaigns. And we were interested in looking at clean background clouds, and this is an example of what some of the clean clouds we sampled, or that were sampled, and smoky clouds in specific. And so we took data, as much as we could find from these different campaigns, and some of the locations of the different clouds we sampled are shown here, with clean clouds in blue and smoky clouds in red. And the key that we wanted to look at were the differences between the clean and polluted cloud properties. So other people, based on previous literature observations, we had expected that smoke would reduce droplet size. And this is exactly what we saw, as you can see shown in this figure here. Smoky data are shown in orange and clean background clouds are shown in blue. And the dark lines show the median values for the bin size classes for smoky and clean clouds. And you can see that the smoke reduced median cloud droplet size by about half. And it pushed the median droplet size away from this this line shown here as the 28 micron droplet diameter, which is a threshold that some have used to mark the point above which precipitation can form and below which it can't. And we also saw that small droplet numbers increased, and these are more susceptible to evaporation. So this is all in line with what previous observations have found, and it just suggests that, that the smoke can lower the probability for precipitation in these clouds. And then we were interested in trying to get numbers that could be relatable to models. And so we used this parameter called the aerosol cloud interaction parameter. We estimated it based on this equation right here. So it's 1/3 times the change in the natural log of cloud droplet number over the change in the natural log of smoke tracer concentrations. And to put this in some kind of context that's more or less easy to understand, the maximum for this value is when every aerosol would nucleate a cloud droplet. And we looked at this in a variety of different parameters that were sampled. So for example, here, this is CCN on the x-axis and cloud droplet number concentration on the y-axis. And what we're interested in is the slope. And we looked at this for a variety of different tracers of smoke. So carbon monoxide, acetonitrile, CCN, backscatter, black carbon, and aerosol number concentration. And we combined these 6 different smoke tracers to obtain a smoke ACI value, which is shown here. So what we found is about half of the maximum possible value. And then we compared this to what models might have predicted the response would have been. And so this is a model from Rich Moore and Thanos Nennis. And on the x-axis is aerosol number concentration, and on the y-axis is the modeled ACI value. And so this star here, this is from the multi-campaign assessment. And it just shows the error bars for the ACI right here. And then here is the range of aerosol number concentrations that we observed. And then we also looked at this case study, which I guess I didn't point that out before, but we did a case study where there was a very intense smoke plume and then some clean clouds outside of the plume that shown here. So we compared this like high concentration event as well, and it actually lined up quite well with what the models observed. So that's encouraging for this type of cloud. But then we wanted to expand the observations into remote sensing data, and this is really important because the remote sensing data are really the best way to observe regional trends, and also spatial and temporal variability, and we really care about the importance of these processes. So shown here is just a cartoon of, just to give you a picture of what we were trying to do. If you're looking down at the Arctic from above, so say for example with MODIS or some other remote sensor, you're going to see a variety of clouds. Some of them are going to be clean clouds, shown here in blue. And in this study, we determined them from calypso and flexpart. I'll talk more about that later. And then some of the clouds that you'll observe, shown here, for example, in brown, are present in very strong aerosol layers. And then some clouds are shown here in purple or somewhere in between. They're not really clean, they're not really polluted, they're just kind of somewhere in the middle. And the average of all these is what you see when you look down at, or the combination of all these when you look down at a MODIS image, for example. And it's fairly easy to look at very polluted cases and say, oh, we see a difference. But to be able to understand what the regional impact is, you need to understand what these average clouds are too, and the combination of clean, polluted, and somewhere in between clouds. That's kind of what our premise is based on. If we can look at the average clouds observed over the Arctic, and if we can isolate the clean cloud properties from them, the difference between the two is what is an estimate of the aerosol cumulative regional microphysical effect on the cloud properties. So this is a metric that's actually directly relatable to observable surface effects, but it doesn't explicitly exclude meteorological covariation. So that's the big problem with it. On the other hand, since it's a regional estimate, it provides regional scale estimates for one thing, and then also because it's regional scale, any local meteorological covariation is hopefully averaged out to some degree. That's the goal. But that is one uncertainty with this method. And for this method to work, it requires a very large sample size that can approximate the full spectrum of environmental conditions. And that's where remote sensing comes in, because then we can get a lot of data from the remote sensing observations. And ideally, you'll also have meteorological data that shows that clean clouds are otherwise comparable to the rest of the clouds. So because the models are just, at the moment anyways, are so uncertain, this method has a lot of value, at least I think so, because it's likely to be more accurate than the current model alone. And so currently we don't have any estimates using in situ observations, to my knowledge. It's mostly based on models for the aerosol indirect effects. So the key though is that it's really essential to identify the clean clouds. This whole thing relies on that. And so we looked into that first. We looked at aerosol observations and also models to help quantify what the detection limit of calypso might be for detecting aerosols over the Arctic. We did this in two different ways. So we did it with aircraft observations here in A. So on the x-axis, we have observed aircraft black carbon. And on the y-axis, we have the fraction of aircraft data that have estimated backscatter that's related to calypso, that's above the theoretical calypso backscatter detection limit. So for example, at high black carbon concentrations, say around 150 nanograms per meter cubed, nearly all the time when the aerosols that have that black carbon at that concentrations had backscatter that would have been above the theoretical calypso detection limit. But when you get down to more dilute concentrations, about maybe a third of the time, calypso wouldn't be expected to detect them based on the theoretical detection limit. And at some point, it doesn't matter whether you detect it or not, because that's just what we call clean clouds, or clean conditions anyways. So this is for nighttime conditions when calypso has the highest ability to detect aerosols. But this is again based on theoretical detection limit, and we don't know if it's relatable to what's observed in the field. So we also looked at this in a different way. We used modeled flexpart black carbon estimates and compared them to clear sky calypso observations at nighttime. And so we can see that at high black carbon concentrations, whenever the model predicted that they should be that high, calypso actually saw that there were aerosols nearly all the time. And at low estimated black carbon concentrations, calypso saw that there were aerosols about 2/3 of the time. And so this could be due to errors in the model itself or to the aerosols not being detected by calypso. So this is sort of an overestimate of the uncertainty, but it looks very, very similar to our other independent estimate. And so from these two things, we kind of get a feeling that even in the best conditions, so nighttime conditions, about a third of the dilute aerosol layers are undetected by calypso alone. So for our purposes, that isn't quite good enough. And so we decided to pare down our observations a little bit to focus really on the most susceptible clouds that are present in conditions that we can determine with very high confidence. And then we would supplement those cases with modeled aerosol output. So what I mean by that is that we focused on optically thin clouds that were present at nighttime. And actually the nighttime focus was also important because we were really trying to isolate, excuse me, we were trying to isolate indirect effects and microphysical effects. And doing it at nighttime allows us to kind of, there's a much lower effect from direct effects or from semi-direct effects. So we could really focus on the microphysical effects. And so we were also looking at predominantly liquid clouds and clouds that had bases of above 0.75 kilometers above the surface, and non-precipitating clouds. And for these clouds, CloudSat data, we looked at Calypso and CloudSat. CloudSat data were only available for clouds with reflectivity above 0.29 decibels. So, and then within this, we to determine whether it was clean or not clean, we also looked at whether FlexPart, whether Calypso observed aerosols, and then whether FlexPart had black carbon below or above 30 nanograms per meter cubed. So with all these basically qualifiers, what this means is that we're only actually able to focus on 5% of clouds. So that was a big downside of this approach. But on the upside, we have very high confidence that we know what's going on with these 5% of clouds. So we focused on these locations shown here. These are the clean clouds shown in blue, and then all clouds shown in gray, and then in red, these are the polluted cloud locations. And we saw some significant differences. All these trends here shown here are significant over sea ice. So obviously we see that there's more mottled black carbon over the polluted clouds shown in orange than in the average clouds shown in gray, and then more in the average clouds than the clean clouds shown in blue. We also saw, interestingly, that cloud optical depth decreased with pollution, and also cloud droplet effective radius decreased, which we would expect. We also saw that in more polluted conditions, there was less precipitation, which other people have also observed. And interestingly, we saw that the percent of clouds that were in mixed phase, as opposed to liquid phase, decreased with aerosols. And so this tells us perhaps a little bit about which freezing mechanisms are important here, at least a little bit, because the observations of decreased precipitation with aerosols is inconsistent with what we would expect if combustion aerosols were acting as ice nucleating particles. But it would be consistent with them either reducing ice nucleating particle efficiency, which other people have hypothesized is maybe the case, or that there's less efficient secondary ice formation related to smaller liquid droplets. But we can't really distinguish which of these two might be causing that. And then we use the SB-DART model to try to understand, how, all else being equal, for example, if there's standard temperature profiles, how might aerosols reduce the regional surface, cloud-based surface heating for sea ice during polar night? And we found that the effect was dominated by changes in cloud optical depth and effective radius. And we saw up to an 8% decrease in heating, not including the cloud fraction effects, which might be substantial. But that wasn't part of the study. So again, this is only for a small percentage of clouds. But I think it's really important because this is a preliminary step towards getting a first regional observation-based estimate of aerosol and direct effects on the Arctic surface. So hopefully, based on this kind of method, we can build upon that and look at larger types of clouds. So that's kind of our goal in the long run. But there's a couple of qualifiers. So I was talking specifically about sea ice, and the reason that is because over open ocean, it gets a lot more complicated. So for example, in the cloud subset that we were looking at, these optically thin, predominantly liquid clouds, we found that over open ocean, this type of cloud is much more likely to overlay another cloud. And that has impacts on how those types of clouds will affect the surface. So for example, here is a sea ice fraction with high sea ice in purple. And you can see the height of the next feature of the below cloud in this figure here. And so 0 would mean that the surface is the next feature, and some other color indicates that there was a cloud basically below the cloud that we observed. So it gets a little more complicated over open ocean. And not only that, but just the trends that we saw, apart from even being multi-layer clouds, were different over open ocean. So while things were generally significant over sea ice, over open ocean, only a few things were significant. So for example, cloud optical depth changes were not significant over open ocean, while they were significant over sea ice. And interestingly, low clouds also appear to be less susceptible to aerosols. So that's indicated here by the green shading. Anywhere you see green shading in this figure, that indicates that clouds with bases below 1.1 kilometers, we didn't see any statistical effect from aerosols, whereas above that we did, or for the average we did. So what this indicates to me is that there's a larger influence of meteorological forcing over aerosol microphysics in low clouds and clouds over the open ocean. And this matters because the Arctic Ocean is changing and we're getting more and more open ocean. And so potentially this means that the effect of aerosols might be decreasing. Yeah, and this could be related to the fact that over sea ice we have a more stable atmosphere, and so the aerosols and the clouds are kind of trapped together, whereas open ocean, it's a more complicated story. So that's kind of a general overview of what we've been doing. For our next steps, well, we understand that there's some evidence that these Arctic aerosols can change cloud fraction by affecting precipitation and in-cloud freezing and potentially the phase. And so we'd like to investigate these processes. And to do so, we're expanding what we did to a larger cloud subset. So our upcoming work, we're going to look at aerosol cumulative impacts on cloud fraction and regional surface radiation over the nighttime Arctic Ocean. And we're going to explore what happens when we loosen the selection criteria to include more clouds, and to see if we can get more representative and useful information on the regional and direct effects to compare with model output. And we're also going to do some further work on the impacts of meteorological covariability. And as a last note, I'd just like to mention that we're very interested in the upcoming Mosaic campaign and the related aircraft campaigns. And we're hoping to be involved in some of them because those can provide us with information on that we can't get from the remote sensing data. For example, what is the cloud phase in some of these thin clouds that Calypso, for example, can't observe. And this will provide us useful information on the freezing mechanisms, for example, in that type of cloud. And in return, perhaps some of the information that we're able to provide from remote sensing can be useful for these aircraft campaigns and for the Mosaic campaign. Because, for example, showing the differences between sea ice and open ocean and low clouds and high clouds might be useful to those campaigns. So we're hoping that we can have some dialogue between ourselves and those groups. And just to finish, here's a few references for the work. And I would also like to, again, thanks the grants that supported this work from NASA. Yeah, and with that, if anyone has any questions, I'm happy to take them. Thank you.
Great, thank you, Lauren. Do we have questions for Lauren from the callers?
Hi, everybody. I did mute people while Lauren was talking, so you may need to unmute yourself.
So, hi, this is Matt Shoup.
Hi.
Hi, Lauren. Fantastic work you've been doing here. Would you mind going back one slide?
Yeah. Here?
Yeah, there we go. I find it interesting. You were speaking a little bit to the phase question.
Mm-hmm.
I get it that, with Calypso, you can identify the liquid mostly, and the liquid's at the top, and there might be ice below that or not. One of the really interesting questions that we have now is how does aerosol impact ice production in clouds, and then thereby controlling the phase of clouds, if you will. And I know you spoke a little bit to this. I just noticed in your kind of bottom panel here, the cleanest clouds have the highest radar reflectivity, which would, to me, suggest the cleanest clouds have perhaps the most ice production. I wonder if you think that might be true in your data, or if you could speak to that at all.
Yeah, we think that might be the case. And it's not entirely clear why that would be, but perhaps it also seems to have some kind of almost reverse lifetime effect, maybe because of the cloud optical depth getting thinner. So it could, I can only hypothesize on why that would be. We don't actually we didn't look at any mechanism specifically, but it could be that it could be related to the size of the particles, that size of the droplets. They're smaller. Smaller droplets might be less likely to freeze. And so that would affect the reflectivity, and that might reflect the cloud optical depth as well, because it might affect the lifetime, or it might affect the ability of these clouds to precipitate. I think in one of your papers, you and your colleagues were saying that some of these the ice helps keep the lifetime of the clouds longer, and so if the aerosols are reducing the droplet size and the ability of ice, then perhaps that could affect the cloud optical depth, which is what we see. It's just a hypothesis. I don't know if that's actually happening, but it'd be interesting to investigate that more, and perhaps with the aircraft data that's coming up and associated with the Mosaic campaign.
Any other questions for Lauren?
So I was just going to make a comment, this is Ralph, which is that we work for NASA, and so we've worked very hard at trying to squeeze the satellite data as much as possible. And Lauren's done a really nice job with it. But the in situ data is absolutely essential for understanding what we can and cannot see with the satellites, which is why that first paper that Lauren presented at the beginning is so important as well. And so that's part of the reason why we are hoping to be involved in those upcoming Arctic campaigns, and why those pieces fit together so well. And many of these questions we can get an indication of based on the statistics from the satellites, but without the in situ measurements, we have much less of an idea of what we're actually seeing. So just a little context there I thought I'd like to add. And
Yeah.
thank you. Nicely done.
Thanks, Ralph. That's great, especially in the context of this meeting. I think with this new Arctic research plan, that's one thing that this collaboration team is really trying to focus on, is bringing together those multi-platform observations for a much more rigorous and confident understanding of these processes. So that's a really good point, and why this work is very relevant to our collaboration team goals. Thanks. Any other questions for Lauren or comments?
Allison, it's Gijs. I'll make a comment that, you know, going along the lines of multiple perspectives, I think some of the things that were presented here are very consistent with what we've seen from surface-based sensors as well. And Matt may have alluded to that already, but looking up at the clouds from below, we see similar relationships with respect to radar reflectivity and pollution levels. And so it's like Lauren said, we don't have the direct measurements to say exactly why that is, but certainly the story is consistent between these different perspectives. And so that's telling, I think.
So now we need to bring the models in to help with that understanding.
Perhaps, although I'm not convinced that the models have all of the correct tools themselves to really get at a lot of these fine details in the clouds.
Other questions or comments? Okay.
Well, I guess one other thing about the planning for the future campaigns, and that is that the satellite component, as qualitative and as statistical as it is, rather than being quantitative and detailed, you know, we're prepared. I mean, Lauren's done some really nice work in this way, and we have some experience in bringing to bear the satellite data. It does require some coordination, and so that's part of the reason that we really would like to be involved in the planning, even though we're not fielding instruments on the aircraft or on the surface. It does require coordination, and it does require some understanding. And in our experience in field campaign work outside of the Arctic, having the models and the satellite people present and involved directly, at least I found, has been a tremendous asset. So we're more than happy to do that if the opportunity comes along.
Hey, Ralph, this is Matt Shoup. So, you know, I can speak a little bit to that as far as Mosaic and some of the aircraft campaigns that will be on that time frame. You know, I would say that we as a community certainly welcome stronger engagement. So I think that perhaps offline, you and I should connect about some of those details. there's a meeting coming up in early October in Germany. That's a meeting of a variety of different aircraft campaign people that are kind of planning aircraft campaigns for the 2019 to 2020 timeframe in the Arctic, a lot of which will be over the sea ice. That I think will provide some very useful information along the lines of what Lauren showed. And then, of course, Mosaic is on the 2020 or 2019, 2020 timeframe as well. So I think there's a lot to coordinate there. And so I'll reach out to you offline and we can kind of talk about a good pathway forward for that.